Let's deriving kinematics formulas. Okay, and so we have a couple left to deal with. All right, so let's just see what we have so far. Okay, so far we have this. We have that velocity is the rate of change in position. We have that acceleration is the rate of change in velocity. Okay, we could take this formula and we can rearrange it into this. Okay, simply by splitting out the delta into the fact that it is VF minus VI, rearranging, we get that. Then we have a formula for dealing with a displacement covered during a changing velocity. And we have two more, we'll call them magic formulas to pull out here. Now, I did not write these in the IB way, so I'm going to rewrite them correctly. So let's just write these properly. Okay. Okay, so this is the way that you would see it in the IB world. This one's okay. They call the final V just V, and the initial velocity U. Don't know why, just do. And then this should be S. Displacement equals U plus V over 2 times T. Okay, so this is what we want. This is how you'll see them. I know it will cause confusion. The problem is, in my other course that I teach, we just call displacement D. Maybe I should switch everything to this. Anyway, whatever. I digress. Okay, so let's write a problem that you would have trouble solving, and then we'll derive an equation to deal with it. Okay. A car at U equals 2 meters per second. So an initial velocity of 2 meters per second accelerates at 2 meters per second squared in 4 seconds. Find D. Actually, you could solve this. It would just take 2 steps. We're going to derive a formula using this as a template to work off of. So let's see what's happening here. Okay, if this is the velocity time graph of this motion, okay, there's U, 2 meters per second. Okay, you know the slope of this is 2 meters per second squared. And what you want to know is, well, how far did it go during this time without first solving for the final velocity, right? If you solve for the final velocity, then you can use this formula right here to solve it, right? But there is a way to get that without actually going and finding what the final velocity is. So we're going to look at that right now. We're going to use it to derive a formula. Okay, so displacement is the area under this graph, isn't it? And if we look, we can divide this up into 2 sections. Okay, so if we don't actually know what this value is, we have this other information, like that this is 4 seconds long, we could, find the area here, and we could add that to the area here. Okay, so let's just see what we have here. The area here is found as U times T, right? Okay, and then how are we going to find the area over here? Well, if this is V and this is U, the height here is simply V minus U, right? And if we want to find the area, we need half of that times T, right? Because we're finding the area of a triangle. So what are we going to do here? Well, we want A plus B, don't we? Total displacement is, oops, call it the right thing, S equals A plus B. So S equals UT plus V minus U over 2, right, times T. Okay, so let's just examine this part a little bit. And let's rewrite it. So we need the height times the base, we need half of it. So there's my height, there's my base, we need half of it. So I could write this as 1/2 v minus u times t. Okay? So this is what I'm interested in right now. Okay? So we know this from our other little formula. We know that, as an aside, delta v, the change in v, is equal to acceleration times time, right? Well, delta v is final minus initial velocity, so it's v minus u equals at, right? Does that make sense? So if I'm looking here, if I see a v minus u, I should be able to substitute in at for that, right? Does that make sense? We agree with this, right? This just comes from here. I should leave a delta on there, I'm not sure. Okay, we'll just leave it as t, okay, time span, okay? So we've just rearranged that formula to solve for v, right? So by multiplying by a, and then we know that delta v is v minus u. So if v minus u is equal to at, when I see a v minus u, I can substitute at in for it. So then I'm going to rewrite this like this: 1/2 at t, right? att. So at times t. We've got two t's multiplying together. What does that equal? T squared. And so what we've done here now is we've rewritten this as 1/2 at squared. And from that, we get this. S equals ut. This area under here is ut, plus the area of the triangle, but written in terms of the accelerated motion, 1/2 at squared. So now we've derived or pulled out another kinematics formula. And we can go ahead and use that to solve this problem. Okay? So it's at 2 meters per second and accelerates at 2 meters per second squared for 4 seconds. So we have this. U. Right? Starts at 4 meters per second. No, sorry, it starts at 2 meters per second. My memory is like that of a squirrel. 2 meters per second times 4 seconds plus 1/2. I say 2 meters per second squared? I did. Okay. Times 4 seconds squared. Let's see what we get. Okay, so we've got 8 meters here, and then we've got 16 times 2 times 1/2, so 16 meters. Okay, so 16 plus 8 should be 24 meters. So 24 meters total. All right, and we can easily like check that against our other formula if we wanted, right? We have 2 meters per second, and we accelerate at 2 meters per second for 4 seconds. So we'll end up going 8 meters per second faster. So 8 meters per second faster, we end up at 10 meters per second, right? 10 meters per second plus 2 meters per second divided by 2 times 4. So 12, 6 times 4, 24 meters. Check. Both formulas agree, and that's what we want, right? So it's a new way to find that without having to first solve for the final velocity, all right? And it has other uses. Obviously, you can rearrange it to solve for any unknown. And you have to also notice that it has the potential to be written in a quadratic format, right? So you could write it like this. Okay, ax squared plus bx plus c. Okay, and I got one more really quickly to pull out of here. And we'll start with another problem. A car accelerates at 2 meters per second squared for 30 meters. Find its final velocity. Okay, so to do this, we don't have a formula that can work with this, so we have to combine two other formulas. So let's go quick here. So this is true, right? Delta V over T, and this is true. Okay, this is just simply rearranging formulas, right? So we're going to start with this. And we're going to square it all. Square, square, square. Actually, sorry. I'm not going to square it quite like that. We're going to square it like this. There. Okay, then we're going to expand. So square the first, 2 times the first times the second. Square the second. Okay, then next step. Okay, well, rewrite it. A squared t squared. Okay. Next. Okay, so I've got 2uat plus a squared t squared. This is where it gets a little bit squirrely. But what I'm going to do is I'm going to pull 2a out of both of these. Okay, so I'm going to divide both of these by 2 and a. So plus 2a. All right, so I pulled 2a out of here, so that just leaves behind a ut. Okay, and a 2a, so one of my a's goes. So I'm at at squared now. But since I also pulled a 2 out of there, it looks like that. Okay, and I'm just going to rewrite it as this. All right. Does that look familiar to you? Did we not just say this? Did we not just figure that out? So where I see this, I can exchange it for this guy. And that brings me to my latest and greatest kinematics formula. And it's the last one. Boom. And now we can solve our problem. So car has a u value, an initial velocity, 2 meters per second. It has an acceleration of 2 meters per second squared, and it covers a distance equal to 30 meters. What's its final velocity? So plug and play. Get about 11 meters per second. Okay, and that's the end.